Well, very good. Good morning again, everyone. My name is Andy Erickson. I'm going to talk very briefly about a project that we have right now that we're wrapping up and the start of phase 2 for this project. This project is biofiltration media optimization. Like I said, so this is a project that I'm working on with my co-lead, Jess Kozarek at the University of Minnesota and St. Anthony Falls Lab. We also have Mike Trojan from the PCA on our project team and Mike Eisensee as well, who are continuing with this and others. And there's actually a much larger project team for this. If I can get it to go, there we go. So we have other people at the University of Minnesota helping with sharing information, creating posters, signage, outreach, things like that, and actually doing some of the work. So that would be Laura Lewis, Barbara Heitkamp, and John Chapman. As I mentioned, Mike Eisensee is also a co-lead on this project. We have Mike Trojan and David Fairbairn on this project. And Aaron Anderson-Wentz is on this first phase for this biofiltration media optimization. And so we have a pretty broad team. We have a lot of expertise coming into this. We had a information gathering session, listening session at the beginning of last year, actually about this time last year, and many of you were part of that, and we really appreciate all of the input that you provided. That actually helped us quite a bit in kind of guiding the trajectory and what we ended up using in our mesocosms, which I'll talk about more today. But the overall objectives for that project, this phase 1 project, was to identify local sources of media, specifically around phosphorus, but we'll get into that. But we also want to look at simple tests or metrics, recognizing that not all compost is the same. Even from the same facility, it can change over time, depending on the time of year, depending on the sources, and especially from different facilities, you're going to get a variety of different types of compost parameters and characteristics. So what we were hoping to do with this project is develop some very simple tests or metrics that either a facility could do themselves, perhaps even a construction inspector could do once the material arrives on site, or some other individual could do to get an idea of the potential for phosphate release. And so that's the idea behind simple tests and metrics. And I'll get into that too as we get further along. But really the three primary criteria that we're trying to compare these different media by is the filtration rate, because in a bioretention facility or biofiltration facility, if you can't get the water through the media, it's not going to succeed. So we need to have good filtration rate. And at the same time, we don't want to have it to be too fast that we don't get any reactive capabilities or processes to actually remove pollutants. We also want it to be able to support plant growth and microbial function in the soil. We recognize that these are vegetated systems, and the vegetation supports a lot of the pollutant removal in these systems, not only through uptake, but by microbial activity in the rhizosphere and in the organic material. We want to be able to denitrify. We want to be able to break down hydrocarbons. We want to be able to transform a lot of these pollutants, or at least sequester them in the media. And so we want to have a reasonable filtration rate. We want to have the vegetation in place. But we also, in Minnesota, are very, very concerned with phosphorus, and specifically phosphate, that dissolved or soluble form. And so we want to make sure that whatever we have as our final design is not something that's susceptible to leaching phosphate out of the media. So for this phase 1, these are kind of our three primary criteria for comparing the media that I'm going to talk about. The way we decided to do this is a couple different types of tests. The first set of tests are mesocosms, which are outdoor tests. We wanted to make sure that we were in the environment. We wanted the vegetation to get as close to the natural environment as it could possibly be. But we also wanted to have a number of different mixes, and we wanted to be able to control the parameters. So we did these mesocosm tests with essentially trash cans. These are about 3 feet tall and about 1 foot in diameter. You can see a picture of the setup here on this slide. We have 30 of these because we decided on doing 10 different mixes and 3 replicates of each mix. Because we also recognize, because it's outdoor, because it's biological, we need to have some replicates. And so we won't get into all the details. We can talk more offline, and you'll see it in the report. we have replicates and replicates and replicates of all kinds of things to make sure that we are having good certainty and confidence in the data that we're collecting. What we were doing then is also using synthetic runoff, simply because we wanted to be able to have control. We didn't want to have to try to wait for the storm. We didn't want to try to instrument this and wait for the rain. In terms of cost, we wanted to be able to run our own experiments on our timetable and control all the parameters. So we did synthetic runoff. We did use river water, Mississippi River water, as our base. It generally had somewhere between 60 to 80 micrograms per liter of phosphorus, sometimes a little bit higher. We would then spike that to get the concentration a bit higher, to be able to get it more in the range of urban stormwater runoff. And then we measured exactly what came out of each of these mesocosms and media mixes to understand what was that potential for phosphorus release. So we measured phosphorus concentration coming in and coming out. We measured the rate at how fast water would come out of these mesocosms. So that replicates essentially what would come out of the underdrains in a biofiltration practice. And then we also tried to capture the vegetation growth in each one of these mesocosms over the entire summer last year from when we were running these experiments. This particular project was limited to an 18-month time frame, so we're only able to get one summer, last summer, out of this. We actually have to turn in our final report by June 30th of this year, but I'll talk about the great news that we got extended for a phase 2 for this project at the end of the presentation. So what did we measure in these mesocosms? So we wanted, again, look at phosphate release was kind of our primary concern with these. So compost was obviously a major component. We looked at both food residue and leaf-based compost. We mixed that at either 10% or 20% with sand, and that's by volume. This is all of these mixes actually came from Plasteads. We wanted to be as consistent as possible. So, and we recognize that a lot of places are getting their materials pre-mixed from Plasteads. So we said, let's just use that as a baseline, so we're not worrying about variability between this facility mixing versus that facility mixing. So all of these were mixed and supplied by Plasteads. Thank you very much for that. As I said, we did 10% and 20% mixed with sand of either food residue compost or leaf-based compost. We also used or evaluated peat as an alternative to compost. We assumed, because this is kind of the guidance in the Stormwater Manual and what we got from our listening session last year, that 20% organic matter is kind of a base that's being used by many of the designers and specifiers out there. So we assumed 20% is our base. So we said, well, what happens if instead of 20% leaf compost, for example, we have 20% sphagnum peat or 20% reed sedge peat? Do we get the same filtration rate? Do we get the same vegetation growth? And do we get the same or less or more phosphate release? And so 20% is kind of our baseline. So that's the organic components. So can we replace leaf compost with sphagnum peat, or how does food residue compost really compare to leaf-based compost? And then we also wanted to look at inorganic additives or enhancements or amendments. And so biochar, that's already come up a number of times in the new introductions here. We already knew that that was kind of a very hot topic here in Minnesota. Again, as there's not really a standard mix out there for biochar. There's a lot of variability, as has already been said. We went with a 15% biochar additive, using, again, 20% leaf-based compost as the base, with the remainder being sand, clean washed filter sand. The reason we chose 15%, it showed up in multiple studies. We wanted to be able to compare it to other studies and see if we were getting the same thing. Biochar possibly has more variability than compost, again, because the sources can be highly variable, but also the manufacturing of biochar can be highly variable. So there's a lot of things that make biochar, but it's a challenge because you need to get something and you need to know exactly what that is and what it can do. And I can talk more offline about the specific details. We used a biochar that was just readily available, again, through Plasteads at 15% biochar 20% leaf compost, and the remainder sand in that mix. Iron, there's a number of iron enhanced sand filters. Again, the standard is 5% iron. We wanted to see what happens if you take 5% iron, mix it throughout the media with 20% leaf compost, and the remainder is sand. So in many systems, we typically try to keep the iron sand separated from the compost mix. We thought, why don't we, since we're doing this controlled experiment, let's see what happens if we mix them together. Can the iron keep up, or does the compost really overpower it, or the fact that it's mixed throughout affect the performance? And then finally, spent lime as another additive or enhancement. Again, that's been something that's been growing in interest here in Minnesota locally. We did 5% spent lime just to be, because it's a similar removal process. It's typically a calcium-based precipitation as opposed to an iron-based adsorption reaction, but it's supposed to be a direct competitor in a way, if you want to think of it that way, to iron, or a replacement to iron. But it is a waste product, so it's reuse, which is great. But again, we've mixed it in fully with 20% leaf compost and the remainder being sand. So these were the mixes. Generally, and we're not at a place where we're comfortable sharing data yet, because we're still going through a lot of the QA/QC. A lot of this project, the end of this project, has been delayed because of COVID, and we can't be physically in the lab analyzing samples or collecting data. We are certainly at the phase where we're analyzing a lot of the data, but all of this has really kind of disrupted this whole project and process. And so we're just not through the QA/QC enough that we'd like to share numbers. What I can tell you is that, first of all, one of the main questions, 10% compost versus 20% compost. If you talk about leaf compost, generally in some of the early data, and again, I can't make any numbers for all of the data yet, but early numbers, obviously 20% compost released more phosphate than 10%. And actually it was at least in the early experiments, close to about double. So it was an interesting, almost linear relationship. And that will come into play when I talk about phase 2. Also, surprisingly, and I think this gets to the variability in composts, the food residue compost, at least in the very early experiments, released less phosphorus than the leaf-based compost. And that was surprising to us. That's not what we expected, but that was something that we saw. Now, again, I can't promise that that's what the final results are going to look like once we get all the data together and kind of start doing our statistics and QA/QC is all finalized, but that was something new that we learned through that. Again, iron seemed to work pretty well. Biochar didn't seem to do much for phosphate. Again, it could be relative to the specific biochar, but there's just a few things, caveats here and there, that we'll be able to get into more detail in the next couple months as we release this final report. So, and as I get more and more specific data that we're ready to share, I anticipate getting this directly to Mike so that he can incorporate that, either share that with the group and or incorporate it into the manual as needed. So that's that part of the experiments. The other type of experiments that I talked about very briefly is this idea of simple tests or metrics for kind of measuring the potential for phosphorus release. And so what we're doing is we're actually considering a number of tests, both analytical tests. So for example, things like Solvita, Brave phosphorus, Olsen phosphorus, Melic 3 phosphorus, things like that, where you might collect some type of sample and send it into a lab. Solvita tests you can actually do yourself. There are test kits that you can purchase and run those yourselves. They're relatively quick and they're actually relatively easy. They may or may not tell you about phosphorus release, and that's what we're trying to measure. We're comparing what Solvita tells you on its rating versus what we actually measure as phosphorus release in a controlled batch leaching experiment like you see in the picture here. And then what we want to do is then measure the relative differences for a few different sources to give an idea of what is that variability. Obviously, that's a challenge because we can't test all of the variety of sources, and we can't test all of the, we can't sample it from all different times of the year because it's a limited scope, limited time period project. But again, the idea was, what's the variability? What are some simple tests that people could do to maybe get an idea of the phosphorus release? And again, this is something that was disrupted by being shelter in place. So we don't have any data to share on this, but we hope to have good information as the project wraps up in phase 1. So again, kind of the objectives, we wanted to measure filtration rate. We'll talk about that in the final report. Again, we saw generally within the first 2 hours for all of these media mixes, upwards of 80% of the water that we added came through. So for the most part, all of these mixes, the way we mix them or the way we receive the mixes and install them, we had pretty good filtration rate, at least for the first year of events. In terms of supporting plant growth and microbial function, we're a little bit disappointed in the plant growth results that we got from this. Again, we don't have numbers to share, but we would hope to get a bit more vegetation growth. We are still looking at the statistics to see if we can determine significant differences between the media, but we're not sure yet. So we'll be able to report more on that as we get through. And then phosphate release, I kind of gave a little bit of that in the slide where I talked about the mesocosm experiments. For phase 2, which we were actually fortunate to get funded, both of these projects were funded through the Minnesota Stormwater Research Council and the Water Resources Center program and the funds that come from the Clean Water Council and the Legacy Amendment. So we're very excited to be able to do phase 2 on this project. As you probably recognize, as I talk about all this, there's a lot of still unanswered questions. The first of that is, can we evaluate these mixes on a multi-year performance? So we have a number of experiments from last year's synthetic runoff events, and because the mesocosms were outdoors, we allowed them to get rained on. And so when it rained on it directly on the mesocosms, the trash cans themselves, we collected the water that flushed out of that. And so you can imagine that would be relatively clean water. It's not runoff, it's direct rainfall. But it's a relatively small amount. But we did get volumes of water out. And so we got a relatively clean flush, if you want to think about that. Hopefully, though, through the next couple summers, we can get multi-year aged media to determine how that phosphate release changes over time. We also want to, as part of that, investigate what happens with phosphate release if you have road salt. And so what we'll do there is actually dose some of these columns with salt in the spring to replicate a snowmelt event. We may also dose these in the late fall. If we get, for example, an early salting event or an early wintry mix event where we need road salt, there's a difference in vegetation. In the spring, vegetation is trying to grow. In the fall, obviously it's the nest, a lot of it's died off. We may get different phosphorus release characteristics in the spring or the fall. So we want to run some salt experiments and see if we get enhanced or increased phosphate release because of salt. We also want to test plant growth, vegetation in low organic content media mixes. So with this first phase, because we were limited in scope and budget, we really only tested 10% and 20%. We still saw a fair amount of phosphate release in the 10% organic content. So we want to test, can you still support vegetation growth at 1% or 3% or 5%? So we're going to do a relatively large block design experiment. We're going to have more replicates. We're going to have a variety of different media mixes and look at how low can you go, really. We're going to play the limbo game with organic content and phosphate release, or really vegetation growth is the primary criteria. And then obviously through all of that, and this is also part of phase 1, but really a big component of phase 2 is take this information and develop guidance and training to get that out and hopefully benefit design and construction oversight in terms of measuring your mixes and your different content that comes in and whether it can release phosphate. So this phase 2 will actually just started. I think I actually just got the executed contract at the end of last week. We go through December of 2022. Ideally, through the shelter in place, if hopefully we can resume some operations, we can do experiments this summer, and we'll get summer of 2020, summer of 2021, and hopefully summer of 2022 in, and then write that project report in the fall of 2022 to get that out by December. So that's kind of the wrap up of the project summary, and I apologize, I'm probably disappointing a lot of people in not having more numbers and graphs in there and data. We will share that as soon as possible. Mike mentioned it, I do want to plug the Minnesota Stormwater Seminar Series. This is a larger series that's bringing nationally recognized experts to Minnesota when we weren't restricted on travel. Now we are going fully virtually online, so you can ignore the joining in person part of this slide. We've had a number of individuals. I actually haven't been able to add Stephanie Hurley's picture to this lineup, but she will be talking tomorrow on bioretention media and amendments, as well as vegetation and holistic design and bioretention practices in general. So if you're interested in that, you can see the link here. I'll also share my slides as a PDF, and that can get sent around to the group, so you can have this link directly. Although again, if you Google Minnesota Stormwater Seminar Series, it should come up as one of the top hits. So if you're interested in that, sign up for that. It is all online through Zoom. We will also be recording it. We actually post all of these on a YouTube channel that we have, and I can share that link as well, and you can watch those in the past ones, or the one that's going to happen tomorrow. You can watch that in the future. We'll have about a 35 to 45 minute presentation from Stephanie on her research and her findings. And then we will have a 1 hour panel discussion with Peter McDonough from Kestrel Design Group, Kate Brauman from the Institute on the Environment in the University of Minnesota, and Rusty Schmidt, actually. For those of you that remember Rusty Schmidt, we still consider him a local Minnesota expert because he basically co-wrote the book on bioretention vegetation. So he's one of our local experts, panel experts. And because the power of digital, we can bring him in to this as a local expert. So he's another panelist along with Stephanie then. So with that, I want to thank you for your attention. If you have questions, I'm happy to answer them. I'm going to pull up Zoom again and see if anybody posted any questions in the chat. If it will let me. Otherwise, you can unmute. Feel free to unmute yourself and just ask questions if you like.
Go ahead, folks. If anybody has questions for Andy, I know I have a few, but I'll hold back mine for now. If somebody else jump in.
Andy. Sorry, this is
Go
David. Thanks for the presentation. It's great. And I'm sorry if I missed this at all, but the two questions I just had about water flow, and I guess one of them was regarding the Mississippi water. Do you expect the constituents to be different, and are you going to characterize that water, relatively for BOD or something else? And then I guess regarding the flow rate through the system, I'm curious if you were going at the sort of annual progressive rate, or if you accelerated the rate of flow. So kind of what that first year of phosphorus leaching from the different media represents in terms of the age of the systems.
Good questions. Yeah, no, those are good questions. So for the first question, for the river water as the background, obviously we expect it to be a little bit different. It's the Mississippi River. Although at this location, where we are at St. Anthony Falls Lab, there is a fair amount of urban landscape immediately upstream, and contributing to that. I would expect, a lot less sediment, obviously, but again, we would actually filter sediment if we were using runoff here, because we don't want to clog it up. We're really worried about filtration rate of just the media and not clogging from sediment. And we want to know about phosphorus release. So sediment, it's actually good we're using river water for that respect. It will have a bit more organic content, potentially. It'll certainly have more algae during certain times of the year. It may or may not have more or less nitrogen. Again, I didn't talk about nitrate at all, but we're actually interested in nitrate, and we did collect samples to measure nitrate. But we are not that concerned about the BOD impact. It could be a bit higher carbon source as well to this, or organic content source a little bit. Although in the river, we'd have in urban runoff, we may have grass clippings. We may have other organic content that's coming in that we may see less of in the river water. So perhaps the algae in the river is a good surrogate as a replacement for that. So we're not too worried about the differences there. And really, it's only going to impact potentially the microbial growth, microbial breakdown, some of the organic content. I don't think the amount of algae that's in the river is more than the amount of sources of other phosphorus potentially in urban runoff. And I don't think it's too less either. And then the second question about loading rates in terms of filtration, hydraulic loading rates, and how much water we're putting in. So we tried to run essentially an experiment every week last year. We obviously had some issues. We couldn't run an experiment when it was raining or the day after it was raining. We could try to run an experiment the day before it rained, but we had to watch the weather and things like that. And there was other factors. What we did, if you look at this picture here, this is the setup. Our green buckets above the mesocosms are our influent buckets. We added approximately 8 inches of depth to each of our mesocosms. And so we assumed kind of if you want to think about it, just a 2-dimensional space or a unit area space. And so we added 8 inches of depth, assuming that was kind of the design storm for these. And so we added 14 design storms to each of these mesocosms throughout the summer last year. And I want to say we had something like 22 rain events, natural rain events. Those obviously didn't fill up 8 inches of water on top of the mesocosms, but they were flushing events. We haven't finished the calculations to figure out, is that overall, if you add all of that together, is that 1 year? Is that 2 years? We did apply for phase 2 because we didn't get nearly as many synthetic events as we had hoped. We had hoped to get on the order of 5 years or possibly 10 years, but we just couldn't do it with all the factors that happened last summer. So that's why we applied for the multi-phase. I feel like this is probably going to be in the 1 to 2 year range of loading, and that's what the data will apply to that comes out in this first final report.
Thanks. Sounds good.
Other questions?
This is Keith Pilgrim. Your spent lime experiment with 5% spent lime, my running hypothesis is that spent lime does take out phosphate because it creates a pH environment rather than kind of actively bind. I think it probably does absorption too. If you take spent lime that's been a treatment cell for a while and you break it, you can see that there's kind of a rind of brown and things are definitely diffusing into it. But I feel like you need enough spent lime to create that pH environment to actually cause the calcium phosphate precipitation, which I think marginally occurs in around 8.5 pH.
Right.
So I expect the 5% might have challenges because of that. I don't really know if it's feasible to do higher percent mixes with that or not, and if that may or may not help. That's just one thought for the future experiments you do. The SELT experiment, my feeling is that iron acts kind of like a big ion exchange resin in these sand filters, and at least the sites we've monitored, I could see that for some reason it's absorbing chloride, maybe in the fall or spring, I'm not sure, but it's definitely releasing in the summer. And so as ion exchange resins work, if you hit it with a really high concentration, it changes how things release. So I'm just thinking ahead, as you add that, you should think about what typical stormwater chloride concentrations are rather than just putting crystals on top of your media. I'm not sure what your plan is, but just a thought. And thirdly, I guess we're slowly gaining experience with organic matter and how these treatment cells work. And, dissolved oxygen, I think, is a scourge for all of these things. And so spent lime, the challenge with spent lime is, I think, when it's direct runoff, you don't have a lot of BOD in that direct runoff. It's a street or something.
Mm-hmm.
And so the spent lime media seems to be working fairly well in that condition. But if you're treating like a pond outlet that has a lot of BOD in it, in these treatment cells, I think what happens is it respires and the pH drops because of it. So I don't know if you're measuring pH or dissolved oxygen in any of these cells, but I think that's a big challenge, particularly spent lime and obviously with iron as well. So I think the fact that you're using Mississippi River water is probably good. It's probably more representative of what's going on out there in terms of where people are placing these treatment cells, just a thought. But direct runoff might have a very different mechanism for how it works. I'm just surprised. We have these treatment cells in the Ramsey, Washington watershed district. They're little cells, and even in a 10-minute period, the dissolved oxygen can be at saturation, and it can be really low at like 2 in 10-minute period, and the pH drops notably. So it amazes me how quickly that decomposition and oxygen consumption and pH change can happen even in a very small treatment cell in a short amount of time. So just some thoughts on my experiences. Thanks.
Yeah, that's great, Keith. You know, actually, we weren't sure how to mix the spent lime, about how much or what ratio to put in there. We kind of thought, well, why don't we try 5%? It is a relatively fine grained material, and it comes kind of as a wet, almost powder. I don't know, Carrie, if you want to chime in, if that was, I know he was worried about that being difficult to mix in the system. But I agree. I don't know what that limit is. If we need to go to 10 to get the pH conditions, if we can realistically go to 10 or 15 or 20% spent lime or not, perhaps that's something we can test in the future. But that is a good comment.
Maybe a simple test where you set it aside for an hour to see how different mixes just cause pH rise. You could just, do a quick experiment like that. And it may be it's just not feasible to have enough in there to cause a pH environment that you need.
And we do have, and this actually kind of answers your last question too a little bit, or your last comment. We do have samples set aside for measuring pH. We have to see, again, scope-wise and budget-wise, we didn't put all of this in to what we were going to, but we have it there available. We may be able to get some data on that. And then salt release, those are good comments, and that's exactly what we plan to do, is use measured or values relative to measured snowmelt. So Bruce Wilson on the St. Paul campus actually worked with MWMO and got some really good data on snowmelt concentrations of chloride and salt. That's based on research that we did actually about 10 years ago now, where we showed that salt pulses into bioretention type mix, compost type mix, will cause a release of metals from compost and potentially a release of phosphate. But it was, the metals part was pretty rigorous. The phosphate was not. So that's why we want to try to do a little more rigorous experiments on that. And we're not going to put crystals. It's going to be a brine, very specifically dosed concentration of salt to represent snowmelt, as opposed to a direct rock salt kind of application. But we did not measure DO on any of these. I agree that would be really, really valuable. But just again, due to scope, we already kind of have this set up. We try to automate it as best we could. You can almost kind of see in this picture, we have digital scales underneath the catchment buckets, the effluent buckets, to be able to kind of record as quickly as we can the change in an outflow over time. But that's about as far as digital automation as we could do in this first phase. In the second phase, we hope to do quite a bit more. So perhaps we can automate some of these things at a relatively low cost. But those are very good comments and suggestions. Thanks, Keith.
Do other folks have questions?
I have a kind of a follow-up question related to the spent lime, discussion. I'm curious if there's literature showing spent lime raising pH into that above 8 range. Maybe it has other things in it that allow it to go beyond 7-ish. But I guess my understanding of lime in most systems is that it creates this buffering capacity where you don't bring the pH much above neutral.
That's a good question, Beth. I'd have to go back and look at the literature that we reviewed, and I know Bar and maybe Greg will talk about this at all, or maybe somebody else from Bar. They did a lot of the lit review or gathering of literature sources. From what I've seen, there's not very much on spent lime. There's a little bit here and there. It's going to depend a little bit on the plant, right, that it comes from, and the source water a little bit, but I'd have to look back to see the details.
Beth, I think the spent lime is made in these treatment plants by using calcium hydroxide. So I think there's some residual hydroxide stuck in that spent lime matrix. I don't have any evidence for that, but I had the same observation as you, that it probably shouldn't raise the pH as much as it does, because sometimes it can raise it up to 9 or even over 9. So I hypothesize that there's hydroxide stuck in there. It's as fancy as I can say. I don't know how else to say it. But so I think that, eventually bleeds out over time. But otherwise, calcium saturated solution calcium carbonate should get you up into the 8s pretty readily by itself. But I think that hydroxide must help, is my guess.
Yeah, the longevity component seems really important. And Andy, you said all of your graphs were kind of linear at this point, and the part where they start diverging from linear is where, I don't know, what I'm hoping to see, where we're looking for. Where is that point? Because then things start actually changing.
Right, I totally agree. Again, that was just some of the preliminary and the early experiments. I do fully expect it to be nonlinear, not only with variations in the mixes, but with time. I don't expect it to be stable throughout the year or consistent. So that's exactly what we're hoping to find is where are these break points, where are these optimization points in these curves and in its lifespan and things like that. So
A super tricky reality of funding cycles.
right, exactly. If only, right? If only we could marry funding cycles with the experiment variability and dynamics.
Other questions?
This is Erin. So I have a question about the compost
Mm-hmm.
release that you were seeing, and you said that the 20% was releasing about 2 times as much as the 10%. So you were seeing a linear relationship. And maybe this is too early for you to say, but did you? And obviously this depends on the goals of any individual filter and plant support. And I'm happy to see you're going to look at plant viability through a range of lower compost percentages. So that's great. I look forward to seeing that. Did you see anything with that phosphorus release rate from the 20% compost that made you think, whoa, everybody stop doing that. Don't do that anymore. That's a bad thing. Are there any big takeaways that you already have in mind, or is it too early to tell?
I think at least in the first several experiments, and this gets to kind of the life, and maybe if there's a possibility to do some pre-processing of compost before we put it in the ground. Absolutely, in my opinion, and even the food residue for that matter, even though it was less than the leaf compost, I would say even both at 10 and 20%, I'd be concerned about the concentrations or the loads, depending on how you want to look at that, coming out in those first few events. I was concerned. It was high for me. Now, I don't know yet, once we get through the QA/QC for the entire year and what it looks like at the end of the year and maybe what the overall load picture looks like, it may be a relatively small part of the entire annual piece of the picture, but at least those first few events, they were pretty high.
Hey, Andy?
Yeah.
And how about the iron treatment with the iron mixed in? Were you seeing phosphorus come out of that one too?
We had really good phosphorus release, phosphorus capture with the iron. So it was counteracting a lot of that phosphate release. I'm trying to remember now, after looking, we've looked at a lot of different graphs and trying to figure out which ones some are releasing, some are capturing. But no, the iron was counteracting a lot of that phosphorus release and actually reducing phosphate from the influent. At least in this media mix. So, but again, we're not sure what the longevity is going to be on that.
And I think you'll see that one of the questions that I listed in the agenda was, what are we going to do about compost? And I'll show later on, I'll show how we've kind of responded in the manual with the known mixes, but there's this bigger question of, is there any situation, I know that we can't answer that yet, but is there any situation in an underdrain system where compost is viable? And
right.
So.
Well, and that's what we hope to answer in phase 2. Can we get to a low limit or can we get to a value that's somewhat optimized to still provide some biological benefit, microbial benefit, vegetation growth, moisture holding capacity, right? But not release nearly as much phosphorus? Or is there some kind of media combination where we can counteract or offset any potential phosphate release from that material.
Well, that's why I was encouraged by what you had said about the iron compost mix. I mean, if that's a viable alternative, then that's great.
Right, and maybe that solves it. But again, I don't want to necessarily be stuck with that either. You know, if people want to try to just go with a low organic content mix, and use something else, for example, spent lime or some other material that might come out, we want to have that flexibility too.
And I had a question then. So in the second phase, you're talking about vegetation at lower concentrations of compost. Are you going to be looking for certain types of vegetation that might be more tolerant?
Yeah, so that's the other aspect of that block design is also potentially looking at different vegetation species. So for this particular experiment, again, we wanted to limit variables. We had limited budget. We had only one summer. We didn't want to have, we just couldn't have as many mixes as we wanted to have. So we only used switchgrass as our single vegetation species in the current phase 1 experiments. In phase 2, we do want to consider other potential species or maybe a mix. You know, there's a MnDOT seed mix. There's all kinds of seed mixes out there, both for bioretention, but also for grass swales and other things. So we want to consider, you know, can we make some slightly different choices about what we put in our bioretention in terms of vegetation that allows us to use less organic content and maybe minimizes the potential for salt. You know, that's the other thing. Maybe we want to look at halophytes and things that are salt tolerant as well, in addition to being able to survive in lower moisture conditions that you would typically have with less organic content. So
Yeah, the North Carolina mix is 3 to 5%, I believe, and I know they say that's tough on the plants, but they're using it, so they must have found some functionality for it. So
right. No, that's certainly what we want to do in the second part is we do want to consider other vegetation species. Obviously, we can't test everything. In our kind of preliminary, when we were putting together the proposal, you know, we were already looking at something on the order of like 500 individual little pots that we're going to do this block design with, just because we want to have a number of replicates and test some different variables. So
we had a question here from Josh. How is biochar performing in your test? And I know you alluded to it not being particularly retentive as for phosphorus, and I think that's what I found in our literature review too. But maybe to add to Josh's question a little bit is it a viable substitute for compost?
right, I would say I can't remember off the top of my head how the biochar mesocosms performed for vegetation. That's really you know, can you use biochar as a replacement for compost? I don't think so, just because biochar is a processed carbon, right? It's not really an organic material anymore. It's organic, but it's not the type of organic that a raw compost or even a peat material would be, right? It will have some moisture holding capacity because of all the micropores and things like that, but it's really intended for removing pollutants. And it's really designed for removing metals, hydrocarbons, taste and odor things, you know, the type of things you'd want to remove with like a Brita granular activated carbon filter, right? But again, I have to look at the data and see, is it reasonable to replace, and this actually, in this particular experiment, we mixed it with compost. So we didn't test it as a replacement directly for compost in these experiments. We could test it in the next phase potentially, but I just don't see how it could do that function.
Yeah, and you alluded to it, the importance of the process that biochar is for developing the biochar, and that's what we found in our literature review too, is that if you form your biochar at lower temperatures, it's probably going to have some nutrient supplying capacity, but then you got to find that balance between leaching phosphorus from the biochar itself too. So it's not, like you said, I think you said biochars, not all biochars are equal. So
right, absolutely not all biochars are equal. And I don't know, maybe Jess can chime in. She's been doing a lot of the QA, QC and statistics on the data that we have so far. I don't think that this particular biochar we were using was releasing phosphorus, but I don't think it was capturing phosphorus either. I could be wrong on that. But yeah, we didn't, again, we're not testing for metals, so But we wanted to throw it in and see what we could measure with this. There's actually a question here that I kind of alluded to as well, but Aaron asked for Kerry, who probably can't see it if he's just on the phone. But Kerry, could you maybe chime in and say, how did the mixing go for spent lime, compost, and sand? And if any of the other mixes either gave you trouble or do you have concerns about?
I think the only mix that we had a problem with was the spent lime. I think it was a little harder to get a hold of. I think that's a supply problem. I know they can't make very much of it. But I think overall, I don't recall them saying that there was a major problem producing any of those materials.
Great.
I think probably the one question, and I did ask Mike, that was the iron aggregate testing.
Right.
I think we're still struggling with the testing specifications and just trying to figure out how should this material be tested, because we're having a magnetation problem and it's adding to the range of the specifications.
Yeah.
This is Kayla.
Yeah.
I had a follow-up question for you, Carrie, or maybe Andy, whoever is better suited, but I'm curious to know where the compost is from, which permitted facility the food waste compost or the yard waste compost is from, and if that compost itself had any testing prior to being mixed. Was it STA certified? Do you have data sheets on that?
Compost that we've used is from Organic Technologies Incorporated and has all been tested.
Thank you.
I think the food source, I don't remember, Andy, where the food source came from.
Yeah, the food residue actually came from SET down in Farmington or Rosemount or wherever their facility is down there. They are an
Okay.
STA. They're one of the 3 STA facilities that you shared with us, Kayla. So that
Thank you.
yeah, but that was a difference between the leaf-based and the food residue, is they came from different facilities. But
And I think if I remember right, the biochar came out of Georgia.
yeah, it was one that you had access to.
Yep.
Andy, did you guys look at the possibility of a green waste or a yard waste based compost?
So the leaf-based compost, and maybe Carrie, I don't know if you have any more information specifically on the source for that leaf-based compost, but that's what I was hoping our leaf-based compost would be, is green waste, yard waste, restricted to that only.
That's what OTI produces.
Okay. Yeah, the only reason I ask is we found that the yard waste based feedstock compost materials have a much higher carbon to phosphorus ratio, so lower phosphorus, higher carbon content, so you're less likely to get any phosphorus release and potential removal, whereas we do see with potential food waste, obviously biosolids, and even leaf waste compost, the potential is higher for that.
So Andy, Dwayne had a question here. As the recipes change, do plants actually have to be part of the system, at least initially?
So we did, for these particular experiments, we did a seeding. We wonder about that, if it would help to use plugs or use some other means. We didn't get into testing that. It is something we could potentially test in our block design if we want to add that variable. But we haven't, I guess I'm not able to give any recommendations based on what we saw for these experiments yet on that particular question.
Well, the reason I ask is that if you can't grow plants, these are starved soils, I can't close out the NPDES permit. But again, there's zero erosion in these ponds too. So I'm in the dilemma to grow something and trying to balance enough water in this desert landscape that you've just created out of this rapid drawdown thing. And sand and other agents that pulse pH potentially in minutes. This is getting more and more complicated to ensure a biological system. But if I can close out a permit, the plants eventually come. No bare soil stays plant free. I can't get it to happen quick enough.
Yeah, and I agree. And that's, that's actually something we saw in this, is we certainly didn't get the vegetation growth that we were expecting or hoping for in this
No.
first season. So I don't know if that kind of confirms what you're saying as well, or corroborates at least. But,
Well, it does. I mean, that's my point here, is that if I had to close out and file the notice of termination on this built facility, I'm not able to get contracts closed because these basins, these droughtscapes, are not working.
right.
And if they are working, I'm probably not draining properly.
Right.
That's the irony, is that I'm getting plant growth, and the plants actually enhance the drainage, but it doesn't happen right away. So I may not see the flow rate that everyone claims, but actually they do flow later on. They're just not initially flowing.
And that's, yeah, go ahead.
Another something I want to mention is that when you start looking at peat, and I've got a site open, I'm trying to again relook at a peat spec. Are you aware that peat can be graded into 5 millimeter fragments? So that you can buy peat from 0 to 5 millimeters, all the way from peat. Again, it still has the small fragments, but up to, let's see what it says here, up to 100 millimeters. And my guess is that the different surface area gives you different release rates.
Yeah.
So the reason I ask that is that I don't have a compost spec that's defined by removing the microsolids. It's just compost.
Right.
So this fraction of compost, or this so-called screening of compost, is not screening for size, but it's getting rid of certain fragments in that, if that might be the more phosphorus releasing agents, as opposed to this more non-labile carbon.
Right.
And then something that Mike Eisensee have talked about a lot is that when you buy compost, I'm convinced that if it's actually finished compost, it doesn't have the release of phosphorus that everyone claims. But I can buy compost using a Solvita test now for your rapid part that is actually looks like compost, smells like compost, but it's raw. I can have also compost the other extreme that's ready to start on fire. It's from one extreme to the other. So we don't have a good way of defining what I'm going to call the aged component of compost. Peat, you might have been in the ground for 8,000 years. Compost might have been turned and blended, and it might actually be several weeks old.
Right.
And still look dark. And I'm not sure that we're actually buying finished aged compost or defined finished aged compost. And maybe Britt could comment on that as well. I don't want to lose compost, in other words, from the recipe. I get that phosphorus may be coming through, but I'm also believing that compost, we know a lot less about compost than we think we do, is my opinion.
Yeah.
Dwayne, I heard my name. Can you repeat the question? Sorry. About compost.
Well, it has to do, Britt, with this idea that that I can buy compost from, let's say, a Solvita 1 to a Solvita 8. And you can take a pile and take the first scoop, might be a Solvita 6. Pretty good stuff. But the next piles I start digging through, the pile of so-called ready-to-sell compost might be varying, again, from 1 to 8 on that Solvita test. Then you stick it in the hole, and I might have a lot of surface area, a lot of basically compost that hasn't reached an endpoint, so that the phosphorus and other beneficial materials have leached out or been denitrified. So basically, I'm buying compost that I'm composting in the sand media. So
yeah.
I'm going to call it the lack of being able to purchase a uniform aged product.
Have you been happy with the quality of that in its use?
Oh, I've been very happy if I use it for roadside growing plants. I'm just not sure it's working. The same thing that I'm buying for uplands are necessarily the right thing for basins.
Right.
And I'm suggesting that we don't know enough about how to screen compost or how to assure load after load after load is the same finished end product. So if you put in relatively early aged compost, I predict it's going to have a lot more nutrient release out of it.
Yes, that is true. The more mature it is and the more aged it is, certainly you'll have less potential release. And in our testing and research, you'll begin if you remove some of the, in addition to that, if you remove some of the fine particles, so you're selecting for larger particles, you actually move from the potential release of phosphorus to the potential removal of phosphorus in those aspects. I guess a couple things too. I'm not a huge fan of the Solvita test. I get that they're a rapid test and something that you can do quickly. Because of that, I like that aspect. But I don't find that they're terribly accurate or as accurate as we need to evaluate true stability and maturity. I prefer the STA, the TMECC test, which is part of STA, to give us a better reading of that. And I realize you got to send that off to the lab and get that information. But
and a good compost producer will be able to selectively take the assay materials and make sure it's really looking good. But remember, I might have 1,000 cubic yards in that particular pile, 100,000 cubic yards in a pile. And depending on how I sample on the outside, I can't go into the core and sample there.
Yeah.
And at least not without a front load or a backhoe.
Right.
So I still need some way to do a rapid assessment for just quality control as materials are being delivered.
Yeah. For that purpose, I like that function and that ability of that test. I just wish it was more accurate. If you're getting, or anybody gets that type of variability from the outside to the inside of the pile, I would not consider that to be a high quality or mature compost, frankly. That's indication that it needs more time and maturity still in process.
Britt, do you have data kind of showing relationships between Solvita and some of these other metrics or tests, maybe ones that are sent in? Because that's kind of a component that we're trying to do with these simple tests and metrics. And that's exactly what we're concerned about, is the variability in Solvita. Can you really rely on that? Can that give you some assurance of the potential for phosphorus leaching, or do we need something better?
I don't have side-by-side comparisons to share. I think a lot of it is just the combination of some experience and then also talking to other folks and discrepancies and results that they've gotten. I'm certainly not ready to say don't use it, because to Dwayne's point, there is no alternative at this point to a rapid in-field test, which is one of the great things about the Solvita test. And I certainly wouldn't want to pull that out as a tool in your toolbox without being able to replace it with something of equal or better value to do spot testing.
Right.
To me, that's the real benefit of that particular test. And I guess it's true for a lot of infield tests, frankly, that are rapid. They're often not as accurate, as reliable as you would get in a standardized lab setting.
Anybody have any other questions?
I just have one. This is Keith Pilgrim. I just have one comment or thought for the iron part of this experiment. Ironically, yesterday I was kind of looking at the Beam Avenue filter construction pictures, and as that thing was put in the sand, it was bright orange, and I'm pretty sure the iron was fully oxidized when it went in. And Beth, maybe you can chime in too, because you've taken samples of these filters. Another filter on Highway 3661, if you dig into that, it looks like a big chunk of iron. It's like elemental iron. It's just not very orange. So I'm wondering, are you adding elemental iron, or are you pre-oxidizing it? Because it could make a big effect, I think, on how it performs in the low oxygen environments. Just a question there.
I guess I'll speak maybe first to these experiments that we're doing, and then if Beth, if you want to chime in on what you saw and observed from samples that you took out. So again, this is actually, we got our mixes from Plasteads, and every time that we've gotten iron aggregate for our experiments from Connolly, which is typically the source, it's come to us relatively oxidized. So it might not be a bright orange, but it's certainly a rusty color. It's an orange color. It's not a gray, metallic, or even a black, right? I've seen some of these filters we've dug into where you're very dark and even black, right, from anaerobic bacteria. So when we get our raw material, it's typically a rusty color. And we've actually, some of the partners we've talked to, they get it at that state as well. Carrie, I don't know if you want to chime in for how you've seen it when it comes to your facility, and then maybe Beth too on what she saw in the field samples.
I would say when it's coming in from Conley, it's definitely more of a rust colored, a reddish tone.
I guess what I'm seeing when I actually do microscopy on these samples is that the rust is rinding a piece of the zero valent iron. So over time, it's going to work its way in and corrode and corrode and corrode until it consumes all of the zero valent iron. So I don't know the status of BNAV when you installed it, for example, but it kind of works its way from the outside to the in, and most of the time what I saw in the filters is that there was still a core of some, some iron remaining to be oxidized, but I guess that is kind of the big longevity question, is how long does it take for these to age? And we have ways of measuring that, but it's definitely not a common practice or even part of the system yet, because it would require more lab testing to kind of know what stages are relevant.
I can also say, Keith, we've been asked quite a few times about alternative sources of iron, right? And alternative products, and certainly waste products that are iron-based or iron aggregates or other such materials. And that has a wide variety of not only how it looks, but that iron content. We've seen some people propose iron media that's only 30% iron, right? And the rest is whatever else it could be. We've seen some that are 90% iron. And again, this actually comes up from Beth's final report. I don't know if the final report from Beth's project has been shared with this whole group, but there's some very interesting information in there about what is reactive with phosphate and what's not in terms of iron mineralogy. So we've certainly seen materials that have come in suggested as an alternative to iron aggregate from Connolly. It has high purity in terms of it has higher iron content, but it doesn't react with phosphorus at all. So that's certainly where we have to be careful. I can't say, I guess we never really recorded it, so I can't say if there's a direct correlation whether it's rusty colored or not. The ones that don't react are not rusty colored, but maybe that's the case.
So one more thing, the only sample that I had that hadn't been deployed of Conley iron was something that Britta had on her desk from William Street Pond. So I was able to take that sample, and it was interesting to me because it clearly had sort of this brown, almost paint job on it. It's like Conley's trying to prevent it, at least for a while, from oxidizing. I talked to them about their cleaning process, and they said it was proprietary, which means I think they're using something simple like Dawn dish soap that cuts all of the greases that are in the system. But it clearly leaves some sort of rind, or they do something to leave some sort of coating on the iron. It's not just a raw steel, to probably prevent it from oxidizing and being a nuisance during transport. So I think at first they're trying to prevent it. I don't, so it depends on how much weathering it's experienced before these go into filter systems or wherever, how much atmospheric exposure they've had, how much rain they've encountered. I mean, all of that's pretty straightforward.
Yeah, we've found at Playsteads that when we make that material, we really don't want to have it sitting here. We'd prefer to have it made and delivered immediately. And we've also found that when we brought material up from Chicago, that we need to put it in van trailers or Conestogas to make sure that the driver understands the stuff can't get wet, because it will seal, solidify in the bag.
Unless there's any other real pressing issues, I probably want to move on here. I just want to show folks a little bit of what is in the manual, because I think we'd like to know if we're on the right track. number one, what are some of the missing pieces and so forth. So I see that I'm able to share screen. So is that okay to move on at this point with everybody? Okay. And I'm sure that folks that have, if there's any follow-up questions that, so I just noticed a comment here by Dwayne that I'm using taconite for my iron sources. So just thought I'd mention that.
In terms
Folks
of,
able to, oh, go ahead, Andy.
I was just going to say, in terms of taconite, actually, I know NRRI at University of Minnesota Duluth has been doing a lot with taconite, and I'm sure Dwayne's familiar with that. But for anybody else that's interested, they have quite a bit of information and resources talking about taconite, and that's been proposed often. The biggest question I have, and I don't know if Dwayne, if you have any references or details or information on it, but I'm always worried about, well, what else is in there, right? And is there any potential for leaching of anything? How consistent is it if it's taconite? Things like that. Those are all the questions I think about with taconite.
We will have results on the leaching, and it's very, very low, actually, very low. But one of the positives that we're looking at least from a road runoff, is also trying to absorb excessive zinc and excessive copper. Zinc from tires, copper from brake lining. So we don't have asbestos, but they're copper lined. So if you think about how many cars, at least normally, would have driven a road, you can end up with a lot of these other metal constituents. And I really don't know whether I want them in my rain gardens or bioswales and living slopes or not. So it looks pretty promising on that. So we haven't seen a lot of other metal leaching out. It appears to be bound, but also I can't say when you flux pH a lot, you know, how these things go from one valent state to another. So I really don't know, because we can only run them in mesocosms as you're doing, but we can't verify how I would know how to salt pulse it or, you know, spill pulse it.
Copperline, huh, Dwayne? Are you a James Taylor fan?
I am, but there's, you know, it's eclectic now of love. And I'm still just trying to fix a hole in my head where the rain's falling in, a classic Beatles song.
Can everybody see my screen okay? Okay. Before I move into the manual though, Carrie, I want to make sure we address your question that you had here. And that is, an engineering firm wants a 95.5 iron aggregate mix sample taken after it has been placed on the job. And if it doesn't meet that spec, wants it removed at our cost. This concerns us because we know the material is difficult to test once it has been produced. Do you have any recommendations? Does anybody have any thoughts about that?
Mike, one of the other comments that I would probably have on it is that the range that we're looking at right now, spec range is 5 to 6. And I just wonder if it's not too tight for this type of a mix. It's really tough to hit that.
Have folks who've worked with this, has there been an experience with that? Any thoughts on this?
I certainly do, and you know, the key here is not to test again.
But what do we do, Dwayne, when we're asked to do it?
Well, when you're this tight, you can't, no matter, and Plaisted is one of the best I know of truly uniformly mixing, but it's still, you know, just like mixing concrete. It comes off these batch conveyor belts. You throw something together and you can get, it's as homogeneous as humanly possible, but depending on how you sample with your little cores, you can actually get a hot spot or a weak spot, and it could be just an inch apart and be that much variation. But in the big picture of the pond, it's perfect. So this is what's unfair about it. So, you know, I'm having to increase the number to ensure that I meet the minimum. Because if you just start at the minimum of 5%, knowing that there's just natural variation, you'll always be off. And I would say that one of the things that Andy should be helping us on, what would be a normal range of error? And
Right.
I think it's unfair
Right.
to say it's a number. It's 5% plus or minus, pick 20% would be fair, but it's something so that you're more realistic. Same thing on compost. You start with something that has bulk densities all over the place. If you even look at
Yep.
peat, it might vary from 200 to 300. Well, what are you buying on any given scoop? Iron is at least a bit more conserved on its weight, bulk density, but I think it's unfair to be absolute without an error percentage within the range of acceptance.
Yep. Thank you.
And I think too, the only thing I'll add to that is actually we have two sources of error. So we have the mixing source, right, and the variability
Yes.
there, and that's what Dwayne said is perfectly accurate. That we are doing it as best we possibly can, right? And whether you're doing it, Carrie, at Playsteads, or somebody's trying to do it in the field, we do the best we can, but we're going to get variability. And we've seen some filters fail because of the mixing on site typically, and that's just what it is. But the
Yep.
second piece, I think, Carrie, that your question gets to also is the testing. How do we measure it? And I know Bar has done some work on this. They've done some experiments and worked with people. And I actually have a letter from Braun Intertech where they've documented when they've tried to measure iron content in these mixes and the challenges therein. So it's kind of a double whammy. We have variability in the mixing process and we have variability in the testing process. And if you get hit with both one way or the other, you could either be way outside of your range or your two errors could offset each other and you just magically happen to land at the right number. But I agree. I think trying to say 5 to 6% is definitely not fair when you account for either of those uncertainties, because the uncertainty there is much higher than both of those.
And another thing is, and Beth can jump into, is elemental iron. If you're taking a backhoe or whatever, measuring this, and you're measuring the weight of this material, it could be actually FeOOH. So it's actually iron with a bunch of oxygens and hydroxides. So, and then you go to the analytical lab and just measure for total iron. So you think you added that much total iron, but you really didn't because it was oxidized iron. So you're going to be off probably by what, 30% there? What's the molecular weight of iron? So you're, I think you're never going to get it right because of that one issue.
And then one last thing that I've seen, and I don't know how to describe it, but it seems like the iron partitions out either on shipping or placement. So it looks like I got a good sand iron blend at the surface, and after one rain event, I swear it's all iron and it's rusted over and I couldn't even drive a 16-penny nail in the surface. I mean, it's that hard. I mean, you don't leave any footprints at all, yet when placed, it was soft. One rain event, it's rock hard. Then it rains again, it becomes sort of soft again.
I think that's been our concern from a supplier, is that especially with some of the specifications going upwards of 8% iron, yeah, these things, they turn into rocks.
And we saw that in some of the original research. There were some kind of pilot scale ones that were built actually coincidentally around ponds as pond perimeter trenches. There was one that was built at 11% iron, 12% iron, another one at 18% iron. And a lot of those high percentage ones, they all locked up. And that's where we kind of recommended that 5 to maybe 8%
Yep.
As kind of that optimal top end of the range. You can certainly go less, right?
Right.
But as Dwayne said too, we're talking 5%, right? 1 part in 20. So whenever you take a sample of that mix, it's quite possible that you're going to get 3% or things like that. It's just, there's some challenges there. So,
Right.
Do we
Yeah,
have
it's difficult because we're looking to hit that 5 to 6 range, and we're at 4.7 or 6.6. It's it's frustrating.
the manual says 5 to 8 right now.
Yeah,
It's-
yeah, I know that the MPCA does, but the spec that we're trying to reach was mandated at 5 to 6, which is really tight.
Yeah.
is it possible, Carrie, for you to maybe push back and say, well, the manual recommends 5 to 8%, and maybe we should change the manual to say maybe 3 to 8% to give us a little bit more leeway there and flexibility. Do you think that's at all possible to maybe try to push back and say it's not very reasonable or practical to try to hit 5 to 6% due to these things?
I think we could certainly try that. Yeah, I've always been tentative about telling a spec writer that they need to relook at their specs, but certainly after this conversation, we should be able to do that.
One of the misleading parts of the design manual, it implies that you're speccing 5, 6, 7, or 8. My recommendation would be that the goal is 5%, but you allow a 20% error on either side of 5%. So rather than saying 3 to 8, I would say 5, but then give them a swing on that for manufacturing purposes, not design purposes. Designers would say 5%. And the reality of the post-placed material is that it might be as low as, I don't know, let's say 4.1 and as high as, I don't know, 7.8 or something like that. So that's just a narrow swing. So I would say 5%.
That's correct. You know, and that's what happens in the golf and athletic industry, is that you're allowed by those testing labs that variance.
Yeah, and this is Erin again, I would think then, you know, as I'm sitting here thinking, well, how would I write a spec now, knowing all that I know and what all we've talked about? I mean, I think, yeah, you would design for 5%. You would set up your bid form so that you're making sure they're buying 5% worth of the iron, and then the testing would have to have a bit more of a range given the difficulty in getting a consistent, you know,
Correct.
sample. But you want to make sure they're buying all that iron and not trying to get
Right.
7 or 3. You know, I would want to be making sure they're paid by the bag or whatever, paid by the ton, and then the testing spec is a little different. So yeah, that's helpful information.
I agree, Erin.
Well, Carrie, feel free to follow up with me if there's something we can do in the manual that would help. And of course, I can touch base with the folks here that have participated too. So.
Okay. Thanks, Mike.
Yep. So I'm just going to real quickly move into some of the stuff that we've been doing in the manual. Greg had mentioned that they executed a work order, and we got back the materials from BAR, and it was a good jumping off point. And when we got the materials from them, I realized this is really a massive undertaking. Trying to identify engineered media, all the stuff that can go into engineered media, getting specifications for it and all that kind of stuff. I mean, any one of these materials that we've talked about is a project unto itself. And we're talking about a dozen different types of materials when you add all the inorganic, organic amendments and so forth and so on. So I'm just going to quickly show you where we're going, and please jump in if you have comments, questions, suggestions. So we have a jumping off page here. And Carrie, I'll try to be as descriptive as I can. So if you look at this page, we've got some general information, so overview of engineered media. And one thing that I've done, and at one of the last SAFL speaker series, Andy, somebody said, we need to take those mixes A, B, E, and F out of the manual. And I just cringed when I heard that, because no, they're not going to go away. But what I did do is I redid the page and the information in the manual. And so now what it says is I've broken it out. So now you've got media mixes for filtration practices. These are under drain systems. And so there you'll see that we're only recommending mixes C and D in the manual. And then you go down and you'll see that we have media mixes for infiltration practices, where you can use any mix that you want for that. And so I think that gets at the concern that particular commenter had, that we've been advertising these mixes, but really haven't been saying what situations they're appropriate for and they're not appropriate for. So I think we've cleaned that up. And of course, the thing that jumps out at you is, well, we've only got 2 mixes right now for filtration systems. And so that begs the question, are we getting close, or are we starting to get close to having enough information to start providing better guidance for what people can do for biofiltration systems? Or do we need to let the research play out a little bit more? Anybody have any thoughts on that at this point?
Yeah, this is Mike Eisensee. So I think I think that this is the most important part of all of the work that's being done right now. I reviewed all the pages that have been developed, and a lot of the information on each of the individual components is really overwhelming and probably not super useful in the industry for designing these basins. But this page is really great, Mike. I think this is a good start, and I would wonder, in June, based on Andy's findings with especially the 10% compost mixes, if we're at a point where we can allow compost infiltration practices. The other piece that's a little bit misleading when I look at the research and I think about design of those biofiltration basins is the MIDS calculator, and the manual encourages the raised underdrain in the system. So we don't see a lot of underdrains at the bottom of these systems anymore. So we always have to remember that the numbers that we're seeing from loss for phosphorus from the bottom of these mesocosms is not directly relatable to the volume we would see coming out of an underdrain that's suspended in a system. So if we can identify a level of compost that we're comfortable with in the fairly simple mixture, then I would hope that would be able to be moved into this bioretention media mixes. And maybe the disclaimer is with a raised underdrain with a minimum of 6 to 12 inches of media below the underdrain. So it has that internal water storage capacity.
Yeah, on this page here, I'm getting the sense that we need to let Andy's research play out all the way before we can come up with specific mixes, but I think we can maybe start going with some recommendations at this point. Does that sound reasonable? Is that kind of what you're saying, Mike? Is that we should know enough in June to at least beef up the guidance on this page?
Correct, yeah, or expand the mixes that are applicable, because I can't actually see right now. If you can scroll down a little bit. So I've never used a mix C or D in a filtration basin, but I have used, we are currently and have been for a number of years been using an 80-20 peat mixture, and it grows vegetation, and we know that the Bray and Olson phosphorus tests of the peat meet the specification for use in filtration without leaching phosphorus. I would like to avoid having peat as the primary recommendation because of the sustainability issue that we've talked about before. So if there's a compost option, that'd be great. But that honestly, for me, would be the preferred mix rather than trying to hit these mixtures of topsoil or more complicated blends and have that variability of the ability for the water to filtrate through the media. That's a bigger concern during construction for us, is can we test the media to make sure that the mixture meets these specs, and then if we put it in and it isn't drawing down within 48 hours, we have to remove the media and try it again. And these are risky mixtures, in my opinion.
Okay. So are you saying maybe you can move mixes A or B up, but with some sort of qualifiers?
Right, qualifiers and both. I think we learned a lot. I think what is mixture? Could you go back down to mixture A real quick? So yeah, so 15 to 25% organic matter. I think what I'm curious with Andy's testing is, what does 10% compost look like? Can we go back to something really specific? Or maybe it's 20, or as an alternate 20% peat, for example. So we get back to something that's specific, and we know what the phosphorus loss is or isn't with a simple mixture. And actually, I wouldn't do A, I would do B, the enhanced filtration blend. Again, I'm not a fan of topsoil in the mixtures because it complicates the mixture and it increases the risk of it not filtering water.
I agree with you on that, Mike.
I'm with Mike too. I don't recommend topsoil because one of the things that nobody wants to talk about in any elephant-filled room is how do you actually build these things and not have any stormwater go to them So it may seem perfect to build last, and it's infeasible to build them last in a typical construction project. So trust me, I'm going to add plenty of soil to it.
But Mike, one of your big differences here is you said you use peat instead of compost, right? Here in this media B mix, the organic content is MnDOT grade 2 compost, right? And you were saying in yours you use peat instead of compost. Is that right? Did I hear
That's
that right?
correct. Yeah, and with the testing that we've done with PlayStats, Carrie's has been running the testing for us whenever we pour up these mixtures, is that they meet the Bray phosphorus guidance in this portion of the manual, and they meet the organic content requirements, and so that's what we've been using, either reed or sphagnum peat.
I guess just to be clear, the criteria though is not Bray phosphorus, right? It's the Melic 3 test, or I guess are you using as equivalent?
Oh, sorry. Yes, I mean Melic 3. Yep. We've run them all.
I'd actually be curious to see what data you have when you run them all, because that is part of what we're looking at is how does Bray, Olson, Melic, some of our simple tests, how do these all compare to each other? So if you already have data where you have a specific compost sample or peat sample, and you have one or more, well, 2 or more of those tests done on that same sample, I'd be really curious to see that data.
Yeah, I've got all of the tests that we've run. It was primarily when I was with Washington Conservation District that Carrie had run for us. I've got them all, so I can send them over.
That'd be great. Thank you so much.
Yeah, and we should expand the information here, I think, and be a little bit more, bring in some of these additional points that you make, Mike. One of the problems that I've run up against with the manual is that sometimes people treat it like it's they have to verbatim, they have to follow everything verbatim, and it's really guidance. And the more information we can put in here, I think the better. If people only knew what was in my head when I put some of this stuff in, they wouldn't use it at all. So
hey, Mike, this is Britt. On the 15 to 30% organic matter, and I guess this would be true for anywhere where you reference organic matter. That's I'm reading that as I scroll down there. You're referencing that as the material percentage of the material rather than the analytical organic matter content in the blend. As an example, compost isn't analytically isn't 100% organic matter. And that's not what you're referencing here, right? It's the material itself.
I'm sorry, can you repeat that again?
I think, Britt, it's referring to the bulk percentage,
Okay.
not percent organic content. It's not percent organic matter as you would define it analytically.
Gotcha.
It's talking about the bulk.
Oh, yeah.
The volume.
Yeah, the bulk volume.
Yeah, and these are by volume. I think that's not clear either. So
just only in a couple places, Mike. In most places, in most mixes, it's actually specified by volume. But there is, I think, actually the one you're looking at, it's not super clear. So
yeah, okay. So we're getting a little low on time, so I'm just going to real quickly jump back to, and Mike mentioned that so we've got these other pages that we put together. So we're looking at inorganic materials, organic materials, and amendments, and we've got our lists of those that we're looking at. So for organic materials, where we've spent most of our time so far, we've looked at biochar and coir. Linnea's looked at wood chips, and Lynn has looked at water treatment residuals. But biochar is probably the most complete example of what these pages look like. And so just very quickly, I'll go through the information. And Mike, you mentioned that it's a little overwhelming, and I agree that it is overwhelming. And we feel to some extent we need to have this in here as a technical support. It's not necessarily that we think that people are going to go to these pages and read every single detail in them, but we feel that it's necessary to have that technical support there if somebody does ask questions. But having said that, we could also do things on these pages that make them maybe a little more useful to people, like put up summary tabs and things like that. But
yeah, Mike, I think that's really the piece that struck me when I was reading this page, is that the overview should be in 4 sentences. What's the practical use and the recommendation for biochar, right? Because when I went through this whole thing, I actually didn't come to any conclusion except for, wow, there's a lot of stuff in here.
There is, and I'm just going to go really quickly through what's in here, and folks can jump in. But there'll be, and every one of these pages is tailored to have the same information. So if we don't have information on something for one of the materials, what the section will say on that page is we couldn't find anything. But every one of these pages is supposed to mirror the other. So coir will look the same as biochar, will look the same as spent lime residuals. And so there's an overview section which generally talks about how the material is produced and what it is, what its applications are in stormwater. And then there'll be a table about applications, the effect of feedstock and production temperature, which is really important for biochar. And then they get into the properties of biochar, the physical chemical properties of it, phosphorus, nitrogen content, and all that kind of stuff. Potential contaminants that you would find in the material. The effects on the physical and chemical properties of soil. Now here's an example, Mike, where there's a summary. And I think what you're saying is maybe let's put one of those at the top of the page so that you don't have to read the whole thing. You kind of get the gist of it. So we have a section on the effect on retention and fate of phosphorus, and then fate of other pollutants, effects on soil physical and hydraulic properties, effect on soil fertility, plant growth, and microbial function. And then standards, classification, testing, and distributors. If we find standards, we'll put them in here. If there's distributors, we have to be a little bit careful with distributors, obviously. What test methods there are there effects of aging of the material, storage, handling, and field application, is the material sustainable, and then there'll be a reference section at the end. So every one of these materials that we're looking at will have the same basic structure to it. And then there'll be a separate table which lists specifications for this. And so for the organic materials, you'll see across the top, you'll see biochar, coir, and so forth. And then on the left, you'll see things like phosphorus leaching, phosphorus retention, handling concerns, and so forth, and all the stuff that I just mentioned on that biochar page. And so for biochar, for example, phosphorus leaching, no. Phosphorus retention, no to slight, based on what we found. Now these can change, obviously. Other handling concerns, and so forth. And then plant, I think the plant issue came up before, and Andy, I think you said that it has some limitations, and here we're saying beneficial but varies with the feedstock. And so so we think these types of tables might be useful too. So that's kind of where we're going, and I guess I'm looking for direction. If folks think that we're just scratching the surface here, there's a lot of these materials, but are we kind of generally headed in the right direction? Any thoughts?
One of the things that's still kind of missing, I don't see it consistent, is that those of us that are trying to spend tax dollars, I have to be consistent on the contract. And so even though you want to be flexible in design, I have to be tight in the specified contract. So it's not clear where I would get standard specs for certain things that we know about. Or reference, so that, you know, even on biochar, when you talk about feedstocks, you talk about the different pyrolysis, I can't tell you, and right now I'm proposing 4 types of biochar. One of them is at 600 degree range, and that's based on what Wenck and the cities are asking me. But there's still use for biochar and for other reasons, not just for infiltration filtration. I'd like to go back, if you would, Mike, to the topsoil blends that Mike Eisensee referred to. And so that what's missing here is that once you write something that I want 80% sand, 20% compost, it doesn't imply that I could have 10% compost and 10% peat. So now if I add iron to it, which constituent changes percentages? So I think that that table should be more flexible so that if you have, let's say it's, and I'm just going to use the type B soil, for example. If you went back there, how do you describe that I could have 80-20, but I could have 80, 10-10, 85, 10, 5. And so I want to be able to somehow allow people to start immediately thinking about when I would add iron, peat, biochar, or spent lime. So this is going to be, is still extremely inflexible. So a well-blended homogeneous mixture of, well, sand, great. But if I added percent organic matter, where does which one changes if I add iron? Which one changes if I add biochar? So I'm looking at this idea that this list would be more flexible in organic matter sources. You know, and you might say, here's the standard, but if I were to add some other things, and I'm really interested in looking at APT sorb materials, so American Peat Technology. So these are engineered peats versus raw peats. Or salvaging mucks, because organics can come from a lot of different sources, and we don't even list when I might add wood chips to these things. So as a designer, I'm just picking mix B, but I don't know from a design where I should have used mix B modified, because there's no real design tool to take input variables and come to a conclusion. I call it as an infiltration decision matrix version of thinking. So I'd like to see this changed a little bit to have organic matter and other infiltration amendments, so that we would know that you want to conserve 80% sand, for example. But how would I know what I'm changing if I don't have a bit more, a way of saying a well-blended, you know, would be 80% sand plus or minus 5% iron plus or minus, you know, those kinds of things. I think this would help to open up a little bit, so you're not just immediately fixed into type B or mix B, and it's got to be 80 and 20. Because you know a designer is going to look at, take mix B and then think no further on it. And I'm trying to say that if you don't think further, it's 80-20. But if you do think further, it's still maybe 85-10-5 with different constituents, from whether it's nitrogen liberation or phosphate retention or microbial benefits or even root microorganism benefits. So a rhizosphere enhancement material, in other words.
So if we modified the manual to be a little more, or even a lot more flexible, the way you're describing, how does that affect the way people do business in any fashion? I don't know. I mean, we can add flexibility, and we can do it in a couple different ways. We can add more discussion. We can.
Well, I like mix B. And I'm just saying organic matter might have other sources. So it just says organic matter, it implies that I can only use compost.
Right, yeah. And
but organics could come from wood chips. Organics could come from peat. It could come from salvaged muck. And so this seems to say that I can only use grade 2 if I'm going to meet the MPCA's requirements for enhanced filtration. And I don't think that's true. So Mike is going to say, I'm going to override that, and I'm going to make you use mix B Eisensee. If you're in my sub area, you know, the middle reach of the St. Croix River thing. So that's where this problem comes in. And I'm trying to build flexibility and restricted ranges, if that makes any sense. So
no, it makes sense to me. And there's a few things to balance in there. Is number one, how much do we know about what other organic materials we can put in? And then,
well, peat and compost are right off the top.
Yep. And then, you know, how much flexibility do we have with the wording in the manual? I don't know. You know, does that, if we really open it up and make, how does it get presented? I guess is a question. That's something that we can explore.
Well, I want to be able to encourage alternative use even if I don't have perfect Erickson results. So at what point do I say I'd like to see 10% biochar? Because I'm going to go there anyway. And I'd like to encourage more iron enhanced materials. So when you do this, what changes?
Yeah, and we could, I think one option would be, so under organic matters, we could say something to the effect, based on our literature review and blah, 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 here are some other options, or something along those lines. Would that be helpful?
Yes. I'm just trying to say that the designer, if you don't know anything, you just pick the mix B 80-20, because that's what we're doing. We're just picking a number. It may be worse than a WAG, but it's sort of like a WAG. And then into something that would encourage the use of these other organics and other mineral-based materials. Because right now, if you look at it, you're basically, I don't even know, no one's going to read this too deeply unless you're a nerd like Mike and Dwayne, or Mike I and Dwayne anyway. But I want to encourage, okay.
Well, I took that as a
Andy
compliment that you were calling me a nerd, and then you took it back. Anyways.
Well, I know Mike I is definitely a nerd, so it helps there. But to encourage the use of these alternative materials. But which one gets sacrificed? If I add 5% iron, which one changes? Do I still have 20% compost? Well, what about 10 and keep 80 sand?
Yeah,
I'm really not going to recommend topsoil. I'm just telling you.
Yeah, I think we can work with that. Now we're past our time. I see. Yeah, some of the folks are starting to leave. So any last remarks that anybody has before we head out? Was this useful information?
Mike, Gary Glatter here. I think it was great information. I think a lot of good things came out of it. A lot of good comments from Dwayne and Aaron and Mike Eisensee. I think overall it's a great meeting. Thank you.
Yeah.
Anybody else? No, go ahead.
Yeah, I agree. I thought it was very helpful. A lot of good information shared.
Okay.
This is Jessica Zarek. I wanted to say thank you for all the input too, and that'll help us as we're moving through the last phase of our project here.
Okay, not hearing anything from anybody. Feel free to contact me or anybody else. I have an email distribution list, which I'd be more than, if you're all willing to be on that and share information as things come across. And then hopefully maybe in a few months, life gets back to, well, it won't get back to normality, but hopefully we can get Andy back out at SAFL doing some work out there. And so maybe in 6 months or so, maybe it might be appropriate to reconvene and see. We'll see how things go. But
Hey, Mike, this is Jay Michaels. I was in another meeting and had to tune in about halfway through. I see it's recording. Is this going to be available?
I believe so. Is that correct, Andy?
Yes, this will be, so I'll share this recording and a PDF of my slides that I presented with Mike, and then he can do whatever he wants to do with it. It'll come as a video file, so I don't know if you want to upload it to YouTube, Mike, or if you just host it directly on the website. That's totally up to you, but it's recorded and I'll share it back with Mike.
Yeah, well, and I'll share it with everybody, and we'll get it, if it's okay with Andy, we'll post it in the manual somewhere.
I'm totally
Excellent. That was an excellent discussion, by the way. It's fun to watch people get worked up over file retention mixes.
Yeah, that's a pretty sad statement, isn't it?
We get by with a little help from our friends, you know.
Well, thanks everybody, and nice seeing everybody, even if it's remote. Everybody have a good day.
Thank you, Mike.
Thank you.
Thank you, everybody.
Just one last question, if you got a second.
Go ahead for me.
Oh, yeah, I was just noting that conversation. One of the things we didn't get to, and I noticed that it was on your web page, is the engineered bioretention media selection tool. I think maybe that's the opportunity to address that variability for designers that Dwayne was asking for. I'm not sure what you had envisioned for that, but I was really excited when I saw that link, but we didn't get a chance to talk about it.
Yeah, well, that's because there isn't much to say other than we do hope to have at some point in time some tool. Are you familiar with the pre-treatment selection tool that was developed?
I'm not. I can check it out though.
Okay, I'm not saying it would look exactly like that, but its functionality might be similar. So basically it would ask you a couple questions, and it would, after you answer those questions, it would point you to an appropriate engineered media mix or something like that.
Okay. Yeah, I'd be interested in that one. And again, I think there's an opportunity that maybe depending on what Andy's test results look like, maybe a 10% media mix with a raised under drain is then a 10%, is a 90-10 compost mixture. If you've got some sort of a setup. So I would be interested in thinking through that with you if you get to the point of actually designing that and putting it together. I think that'd be very useful.
Yeah, we'll get there someday. So.
Okay.
And honestly, I foresee I'd like to convene a meeting, and I don't know if that's just a meeting of our project team or if it's broader than that, like our listening session that we had before, to talk about the results in detail and see if you see things that we didn't see, or if you see recommendations based on that. I'm always hesitant to kind of recommend blindly, or maybe in a silo, maybe that's a better word, to the design community based on research. I like to get input. So I foresee us sharing a lot of this information with you and getting what you see as recommendations for how it changes design.
Whether you call it blind or wild, it doesn't really matter. I'm having to move forward with wild AGs, whether it's a blind AG or not.
Yeah, that's possible. Yeah.
Okay, good, great. Well, hey, thanks. I just wanted to point that out at the end there before we all left. But thank you so much. It was a great meeting, Mike and Andy.
Thanks again, everybody.
Thank you.
Thank you.